everybody, this is final presentation. I gonna show you two problems of chapter 5. First of all, I will talk about problem number 1. As you know, lenses are used in many applications requiring the manipulation of light wave. We have different type of lens will either refract light to a point called a focus point, or they may cause the light wave to diverge outward. Shows the 6 type of lens used in optics. The lenses are sorted into negative lenses and positive lenses. This problem wants us to show these 3 lenses are positive and these 3 lenses are negative. The physical property of the lens N, R1 and R2 can be combined in a single number f called the focal length, which is defined by this relation. To determine whether a lens is positive or negative, we need only determine whether its focal length is positive or negative. Before explaining the positive lens and negative lens, we have to know that R1 is the radius of curvature of the left-hand surface of the lens, which is positive number, and R2 radius of curvature of the right-hand surface, which is negative number. Positive lens, you can see the left side is positive lens, are thicker at the center than at the edge. Light from this lens is focused to a point in front of the lens. It produces a real image which can be projected onto a screen, while negative lenses are thinner at the center than the edge. When parallel lights pass through a negative lens, they spread out from a point behind the lens. The distance from this point to the center line of the lens is the focal length. This lens cannot bring parallel light together, so it produced a virtual image instead of real image. One of the important factors should be considered for lens is lens aberration. When dealing with lens, the basic materials from which they are made have variation which have an effect on the way light behave. This is mainly related to reflective index and dispersion of the glass. Due to reflection and dispersion, the lens won't be able to focus the different wavelengths at the exact same point as the focal point. This type of effect is known as chromatic lens, which produce a blurry image. And for a spherical aberration, a lens are made with a spherical surface light ray that are parallel but at different distance from the optical axis will fail to converge at the same point. The effect of aberration can be corrected by utilizing multiple lens system known as compound lens. Let's go to our case. For double convex, which is positive lens and produce a real image in front of lens, we have focal length and R1 is positive, but R2 is negative. Double concave is a negative lens which produces virtual image behind the lens by negative focal length. And for the other lens, which is positive and negative, you can see for each case we have different focal point. Let's go to simulation using MATLAB. First of all, I set option for ray tracing, then make function for optical system and make ray, and define color for each ray, then define the optical system for each case, and at the end trace all the ray. The results can be shown in next page. I only simulate the positive lens, which focal length is positive, and the focal points for each case is different. All the image is real image, which is in front of lens. As you can see, each lens gives us a different focal point. Go to another problem, problem number 7. A normally incident unit amplitude monochromatic plane wave illustrates a converging lens of 5 cm diameter and 2 meters focal length. 1 meter behind the lens and center on the lens axis is place an object with amplitude transmittance is given by this relation, with the other parameters, and wants us to sketch the intensity distribution across the u-axis of the focal plane. Go to mathematical solution first of all. For mathematical solution, as the projected pupil function of the lens is considerably larger than the finite size of the object, we can neglect it. And then we have the following expression for the field in the focal plane, UF, which is given by this relation. And we get UF from the equation 522. And then by adapting equation from chapter 4, 436 to this problem, we can get the intensity, which is given by this relation. And for calculating some parameters, lambda d over L, f0 lambda d, we have this parameter. Okay, the results presented in equation 522 is essentially the same results obtained when input was placed directly against the lens itself. By increasing the distance from the focal plane, the size of the transform is made larger, at least until the transparency is directly against the lens, means d equal f. By decreasing the scale of the transform is made smaller. A plot of the normalized intensity pattern is shown by this figure, which is the right side with all distance expressed in meters. Okay, go to MATLAB code for this problem. First of all, we define some parameters, which also problem gives us this parameter. Then we mention the amplitude transmittance, and using a Fourier transform function FFT shift, then we represent the field distribution, and at the end the intensity. By running this code, we can get these results, which will be like this. The left side is mathematical solution and the right side is related to simulation. As you can see, the both results are near each other and the same. Okay, what we learned in this chapter, we learn how to dealing with different lengths and imaging a system. Thank you so much for attention.